Hi, everybody, and welcome. Today is Thursday, May 20th. Today we're covering chapter 34. Chapter 33 and chapter 34 used to be basically done together because the ideas are similar in a sense. Both of them deal basically with transformations or the nuclear reactions that nuclei basically go through. For the most part, the chapter 33 dealt with radioactivity, which is really more of a natural process that happens on its own. Chapter 34 deals with the unnatural processes, basically the ones that are man-made, like for example, when we, for the case of fission and fusion. And also, in some sense, also fusion occurs, for example, in the core of the stars. So that's actually a natural process too. So again, chapter 34 deals mainly with fusion and fission. Let me tell you where we stand and everything else also in terms of the class. We still have chapters 35 and 36, and they're actually going to be combined for the fact that both of them deal with relativity, albeit one of them treats it from the special theory, basically, and because it gives us a different way of looking at mechanics for objects that are moving too fast. At that point, we will be confronting an issue in the sense that objects, I mean, if they move, they cannot really move with an infinite speed, because if they do that, then we will have events that happen in the same instant everywhere in the universe. And that is a problem in terms of causality, because it's going to be an issue. So in this case, there is a limitation on how much things can move with, and that limitation turned out to be the speed of light. So that is the special theory, and it treats from that point on everything else that follows from it. There are some very, very important conclusions based on that. One of them, things that were intuitive, for example, when things move relative with one another, we have an intuition. Let's say, for example, you are in a train, and the train is going 50 miles per hour, and you're jogging at the train with 10 miles per hour. Then our intuition tells us your speed, if you're moving in the same direction as the train is moving, is 60 miles per hour. Whereas when we come to this kind of physics, basically in special theory, when it comes to speeds that are super high, you cannot exceed the speed limit, the speed limit of light, even under those conditions. So in a train that is moving almost with the speed of light, and you're running at almost the speed of light, your speed is not going to be any greater than the speed of light, no matter how you do it. So there are some things that are intuitive that fall apart. So this is part of chapter 35. Actually, chapter 36 takes that to a further extent and comes up with a generalization in a sense that gravity and also acceleration, they are in a sense similar. And that leads to a generalization in here between the so-called inertial mass and also gravitational mass, which was something that was noted all along to mechanics of Mr. Newton, that it was true. This leads to a lot of weird things, like, for example, time dilation and length contraction, and a lot of paradoxes, like, for example, the twin paradox, the too big to fit in. Like, for example, if you have a ladder that is, let's say, for example, it's a meter long, and you have a space to put it in, which is only 50 centimeters in, how can you do it? You can actually, if one of them is moving super fast, there is the length that contracts and it should fall into it. So there are things of this nature that seems to at least contradict our intuition. But even though they're contradictory to our intuition, they're actually true. Case in point, your GPS would not work on your phone without this kind of mechanics, namely the relativity. So this is topic for next week, namely for Tuesday. After that, we're done with the content. So next Thursday, if some of you would want to meet, please email me ahead of time or message me ahead of time so that we can meet. We can do it in a group meeting if you guys have questions, especially related to the assignments that you have, or we can meet on an individual basis if you have specific issues related to what you're doing, so that you would want to address them in some sort of a private setting. Please let me know so that I can arrange for that. Other than that, there is no basically class after this coming Tuesday. So everything will be done in terms of content. There is a review that I'm working on to publish for you guys, so please watch it. The review is actually graded also for participation, so please also go through that. And then the last exam is sometime early in June, okay? I think the latest we can do this exam in here is June 10th. I know I made an announcement before in the syllabus, so it may be open before that due date. And of course, if you would want to work on it toward the end, that's fine. It is similar to the previous exam in a sense that there will be a window when it's open. You cannot start it unless you are fully rested in a sense that you're ready for it. Let's say, for example, it's 2.5 hours. You cannot start the exam until you have at least that much time available for you to take the exam, because you cannot start it and then decide to stop and then come back to it. And then the other thing also to remember is that your exam is individualized. It's coming from a huge data bank of the questions, that is. So you and your somebody else will have completely different questions. So there is no way that you're going to have similar questions. That's why make sure you do the review, make sure you're at ease with everything in here. It's only covering the second session of the exam. It's not covering the first. So it's not a comprehensive exam. Once you're ready, then you think that you have the time to go through it, and that's the end of it. That's the whole thing in terms of what we have. This chapter today is kind of light, so we'll try to make it interesting, okay? So I'll try to have it interesting. And then the next chapter is going on Tuesday, is going to be the last big one, and that's it. So let me pull my share screen in here. So this is basically part of the presentation that I did last time, that we started last time. And this deals basically with the nuclear fusion and fission. And nuclear fusion, let me explain the process again about what happened, if you guys remember from the discussion last time. So we have two competing forces inside the nucleus. And the two competing forces are the attractive force due to the nuclear force, the strong nuclear force, and it's attractive regardless of what type of nucleon you have. It's a proton or a neutron, there is an attraction between them, regardless, end of the story. And the messenger of the force, in this case, it's called the gluon, okay? Yes, or they are not. Well, the gluons, they are inside the quarks, so probably some sort of mesons. Anyway, I think they are the gluons too in here in this case too. Anyway, so in this case, you have the atom and the nucleus in this case being put together. That is what is responsible for bringing them together. On the other hand, you have a repulsive force due to Mr. Coulomb's force, and that is because you still have positive protons next to one another, and they will repel one another because they have similar charges. So there is a competition between an attractive force, which is stronger on a short-range order, and a repulsive force that doesn't care about the distance. It's always repulsive. So as the distance, as the size of the nucleus becomes bigger and bigger, the protons on the opposite side of it will become far away, in such a way they're actually not feeling the attraction as much as the repulsion due to the electrostatic force. This atom now is ready, is ripe. If it is disturbed somehow a little bit, let's say, for example, it collides with a neutron, then in this case, that's enough for it to disturb it so that the whole basically nucleus splits apart. So the fission happens for extremely heavy nuclides, and now, depending on which one you would want, that depends really on the amount of energy you're going to get of it. If you really want to produce energy off of it, you would want to have it the most efficient process. So you need an abundant fuel, an abundant basically source of energy, plus an easy way of converting that energy, that fuel into energy, basically using this process and controlling the reaction, because it could very well be, could get out of hand and becomes basically an uncontrolled nuclear reaction, in which case it becomes a bomb, okay? You don't want that scenario, so you'd want it to have it controlled. So the technology is kind of very hard actually to do, and it's very hard from several aspects. First of all, getting the fuel itself, Most of the time we used uranium-235, at least in the beginning, that's what we were using, until we ended up finding that a byproduct of that reaction is plutonium-238, because the products that come out of the uranium-235 interacts with uranium-238, converting it into plutonium, and plutonium actually is as good as uranium-235. So you could make fuel as you go. You could make basically more and more of what you need to make energy basically as you go. So this is basically how the fission works, the splitting of the atoms work. So again, this is the process. This is uranium-235, okay? So it captures a neutron coming at high speed, of course, coming with a kinetic energy. So you need a little bit of energy to get this thing started. Now the byproduct in here is any of these elements in here, in this case, krypton and they split more or less evenly. And then one of the things that you get from it is 3 more neutrons. Now these neutrons, they come super fast, meaning they have a tremendous amount of kinetic energy. You can use one of them or all of them to trigger more nuclear reactions like this one. So if you use all of them, you have an uncontrolled, basically, nuclear reaction in this case, because it can go exponentially up rapid, because from 1, you make 3, from 3, you make 9, from 9, you make 81, from 81, you do the math, 81 squared, okay? And so on and so forth. So very quickly. But now, if you control this reaction and capture some of this neutrons, then in this case, you just will make however you want. Depending on the temperature you would want to achieve in the reactor, you can basically, if you want to kill the whole nuclear reaction, you can send the rods all the way inside, which means they will capture all the escaping neutrons, and in this case, you're done, okay? Or you can pull them up a little so that you expedite the nuclear reaction, so that it will be faster and faster, but you don't want to pull them all the way because the nuclear reactor could explode in this case. So this is the chain reaction I was describing in here. So the process could, in this case, from 1, so those are the byproducts, you can end up with 2, 2 gives you 4, and so on and so forth, okay? But you can control it or not control it, okay? So chain reaction is in uranium, small amount of chain reaction fizzles, critical amount chain reaction produces an explosion. So if you would want to really make a bomb, you have to make sure that you have this proper ratio in here. Otherwise, it's basically going to die out quickly. Can I leave it to you guys to go through the discussion questions in here? A lot of questions in here. So this is a typical bomb in here, a bomb in which pieces of uranium are driven together in so-called gun-type weapon, as opposed to the implosion, basically, weapon. So depending on how much basically uranium-235 you have in here, you may have to basically trigger the bomb with an explosion, or if you have a lot of it, then it's going to explode. This is basically the bomb principle for it. This is a reactor. Now, reactor converts again nuclear energy into thermal energy, and from thermal energy, it's going to become, namely heat. That's what it is. It goes into becoming a electrical energy. So you can make electricity out of it. In the United States, 20% of the energy is produced using nuclear energy, whereas in other countries it can be as high as 75%, for example, in France and other places. So the ratio of uranium-238 to 35 is not really that great, in a sense of most of the uranium that you find in the mines is actually uranium-238. Uranium-238 is useless when it comes to this nuclear reaction. So you really need uranium-235. So you need a way for you to separate both of them, okay? The rods are made out of neutron-absorbing materials like cadmium or boron. In this case, they absorb the uranium. So you really need to, and the water surrounding nuclear fuel is kept under pressure to keep it at high temperature while it's in use. So here is a nuclear reactor, typical nuclear reactor, and how it looks like. Okay, I have had the chance to go to some of these laboratory ones, of course, without this boiling water and all of the other, without this boiler, basically, without the rest of the energy production. So basically what you have in here, you have these rods, okay? And these rods, after a while, they need to be replaced because they have absorbed to their fill the neutrons. So you really need to replace them. And also the fuel rods themselves need to be replaced because at some point they become depleted out of their uranium-235. So in here, imagine with me that somehow the nuclear reaction gets triggered, okay? So there will be a lot of basically escaping particles in here, namely especially neutrons, that are moving super fast. And when they move super fast in this fluid, they increase its temperature. This fluid now is actually very radioactive because it has a lot of radioactivity in it, and mainly it's actually neutrons. As a matter of fact, if you have had a chance to go and visit one of them, if you look down on the fluid, and if there is an access to it, usually when you go in, there is all kinds of Geiger Miller counters and making sure that the radiation is not too high. What you see that there is this bluish color, okay, that comes off of it. And what that is going on is that the particles that are escaping from here are moving super fast, even faster than the speed of light inside the water, because light inside the water moves a lot slower, moves about 200,000 kilometers per second, not 300,000. So the particles that emanate from it are moving faster than that, and that what gives you that it's like a plane going supersonic, basically. This is similar to it. They're moving faster than light, and the light in this case gives you that blue color, and it's called actually the Cherenkov effect. That's the name of the effect that you see in them. So now the temperature has increased, and since the temperature has increased, you can the vapor that comes off of it in here goes through this exchanger and inside this boiler. Now this one grabs the heat. Both of them are insulated from one another in terms of contact between the two fluids, but the heat is exchanged. There is a heat exchange in here. So the water that was in here sitting at low temperature starts to boil, basically, hence the name boiler. So now the steam that comes out in here turns the turbine, and the turbine basically is magnet and a coil moving with respect to one another. And then according to Faraday's law, you will induce an EMF, and that EMF is exactly the power that you receive in your household. So that is basically how the power generation comes in. After going through this mechanism, the steam that comes out loses its energy because of the fact that it's driving these turbines. And the turbine is going through the generator and so on and so forth. So it loses energy and basically condenses. It goes through another condenser actually to lose more of its energy, and it's compressed and sent back into the chamber to go through the cycle. The same thing in here. This loses energy to the water. This fluid loses energy to this water, and then its temperature decreases. Again, it's sent through this process again to heat up, and the process repeats every cycle. As I said before, the control rods, they are made out of the materials that absorb neutrons. So if you would want to kill the nuclear reaction and shut it down completely, all you have to do is push them all the way down. Once you push them all the way down, the escaping neutrons, they're captured by these rods, and there is no nuclear reaction. So basically you stopped it at its tracks. If you would want to start it, you have to pull them up slowly, and basically monitor the temperatures and monitor everything to make sure that everything is correct until you have reached the operational level. At that point, you're satisfied with it working the way it's supposed to be working. So this is how nuclear reactor basically works using the principle of fission, okay? Fusion, still we are working on it. We really don't have any operational nuclear fusion reactor, because if we do, we would have access to a huge amount of energy with very little cost, basically, because hydrogen exists in far more abundance than the uranium-235, and does not require very complicated ways of extracting it from, for example, water, because remember, water is H2O, which is mainly hydrogen. Anyway, so this is the same process as described before. Now, plutonium-239, as I said before, is produced in the same nuclear reactor, and that plutonium-239 will go the similar process. Actually, it acts exactly like uranium-235 when it comes to fission. Okay, in other words, in a breeder reactor, which produces plutonium-239 out of uranium-238, while consuming uranium-235, it's going to make more plutonium-239 than it takes uranium-235. That's why it's called the breeder reactor, because it makes more fuel than it takes, okay? And energy also. So they're very, very smart device for that, okay? Okay, what are the benefits, of course, for nuclear, for a fission nuclear reactor? First of all, the energy, produce a lot of energy. You don't produce carbon dioxide, and you don't contribute to the ozone, basically depletion. So in other words, the pollution is minimized in here. While the drawbacks, of course, you could have radioactive isotopes that are probably released. So you really have to have a handle over that. Or it could be in the hands of some people who wish harm to other people, and they can use it to their disadvantage, okay? So again, where is that energy coming from? It's coming basically from E equals to mc squared. All energy is coming from this equation, as a matter of fact, even the chemical reactions. In the chemical reaction, the process is so converting a very tiny amount of mass that it is negligible on the scale of the mass. So that's why the mass looks like it's conserved, but it is not. Any reaction that produces energy, any exothermic reaction that produces energy, actually is converting some of the mass. There is a missing mass in this case. Any reaction that consumes energy is actually taking more mass. If you weigh the outward, in this case, it's going to have more mass than the inside, the products. That is for the endothermic reaction. For the exothermic reaction, it's always the other way around, in the sense that if you add the mass of the reactants, they are more massive than the products, and the difference in mass, which is the missing mass, is the energy, basically, according to this expression. Obviously, you don't need a huge amount of mass to convert it to get into enough energy, because this equation has c squared in it, and c squared is a huge number. Remember, c is 300,000 kilometers per second, and you have to use meters, so it's 300 million meters per second. When you square it, that's going to be 9 times 10 to the power 16. That's a huge number. So even with a tiny mass, you could end up with a huge energy. So that's the idea behind it. So the first thing is, now we need to understand is how to isolate this, and how to know their properties. One way of doing it is by taking material, it doesn't matter. For example, uranium. Uranium has the same chemical properties. In other words, has the same number of electrons in its outer shell. It has 92 electrons. Whether you need uranium-235 or uranium-238, they both have the same number of electrons, because they have the same number of protons. Where they differ between one another is actually in the uranium-238 has 3 more neutrons than uranium-235. So uranium-238 is a little bit more massive than uranium-235, more mass, okay? It has a little bit different physical properties, but chemically they have the same property. So if you run this material through an ionizer, basically you strip one of the electrons of them, put them in their difference of potential, or you heat them up, whatever process you might think of. Now, as they emerge from it, they emerge from a charged, number one. Charged, but you would want to give them velocity too, so we would want to accelerate them. One way of accelerating a charge is putting it inside an electric field. If you take charges and you run them through an electric field, this is, for example, the cathode, and this is the anode. Since they lost electrons, in this case, they're positively charged, so they are pushed from the anode toward the cathode. So if they're running through this, we'll make an opening so that they come out from the other side. However, there is a problem with this process, and the problem is the following. Because some of them are moving faster than the others, they really don't have the same velocity, and you would want to have the same velocity. So you run them through another device called the velocity selector, and the velocity selector will basically kill all the velocities except one velocity out of all of the ions that emerge off of it. Remember, I have 2 types of ions now. They are the same material, so the same charge, but they have different masses. That's the only thing that is going different. So what the velocity selector is 2 plates of a capacitor that are at different potential. Namely, one of them is a higher potential than the other. And then in the same region of space, there is a magnetic field also. For these 2 fields, they work against one another. One of them trying to bend the charges downward, the other one is trying to bend the charges upward. And where the velocity, so some of the ones that are moving too slow, they will bend under the effect of the electric field and end up in the positive plates. No, I'm sorry, in the negative plate, because they're positively charged, okay? Whereas the ones that are moving too fast, they will be bent by the magnetic field actually onto the upper plate, okay? Against their own will, because they're moving too fast, and the magnetic field in this case is proportional to the velocity. The ones that have their velocity exactly the ratio of the electric field over the velocity are the ones that are going to emerge through unscathed, completely unimpeded. So now you have the same charge and you have the same velocity, but different masses. As they go through the last stage of the process, in this case, they will be bent according to their inertia. The lighter particle will be bent less than the heavier particle because it has more inertia. Takes a long time to go around under the magnetic field. Now, this is a different magnetic field. This is not part of the velocity selector. So in this case, what happened, you have two isotopes sitting next to one another. One of them, 235, for example, the other one is 238. The same thing between carbon 12 and other materials in here, whatever you're going to isolate in here. So the different masses that will be laid out on a different points in here where you go and collect them. This is called the mass spectrometer. This device is called the mass spectrometer, okay? Obviously, this is not an industrial way, really. This is more of a lab way of doing the separation. In the industry, they use a different process. They use a centrifuges, and the centrifuge is just like what is used for the plasma in the hospitals to separate basically the lighter element versus the heavier element. And then the more you run it through the centrifuge and the faster it moves, spins, of course, you're going to collect one of them. You're going to enrich it. That's basically what the word is. You're going to enrich your sample more and more every time you run it through a centrifuge until you end up with a high enough dose of your uranium-235 separated from your 238. And in that case, it's whether or not it reaches critical mass or not for a bomb or for a nuclear reactor. That's up to your applications, okay? So that is how the industry actually separates the fuel in this case. Again, as the atomic number is basically increases on the periodic table. Of course, the nuclear mass also increases because more and more nuclei is coming in here. And it's more or less linear. Actually, it slightly deviates from the linear after a while because of the binding energy inside the nucleus. And here is, if you calculate the energy for every atom on the periodic table, every atom, every nucleus of the atoms on the periodic table. Here is the problem. And divide by the number of nucleons. For a hydrogen, it's easy. It's only one atom, so there is no point for it. Next element is actually helium. Helium, you have 4 nucleons. And if you find the energy that is for that, if you find the entire mass, and you divide it by 4, you will find the number. And the number sits in here somewhere, okay, on this line. You go to lithium, it sits in here. You go to all of the elements, carbon is here somewhere, oxygen is here, and you continue, you find iron in here. Iron has basically the most, if you wish, the least, if you want to continue this way, the least energy per number of nucleons in here. If you look at it this way, that means that it lost most of the energy needed to lose to produce iron. At the same time, now you start to grow, actually. You start to go on this line, and now it starts to grow. So it seems like we're losing less and less as we move on. Obviously, the lighter elements in here seems to move faster toward iron, whereas the heavier elements in here seem to move slower toward iron. That means that I can convert this element, if I can bring it down on this line in here, like fission, for example, or breaking it down, I will gain that extra energy in here per nucleon. Same thing. If I fuse this element in here and come down on this line, I'm going to gain that much energy per nucleon. And that is basically the principle of fusion and fission. Stars do this. Stars, they fuse elements on their own. A main sequence star like the sun, for example, converts hydrogen into helium. So it goes from here all the way to here somewhere in its main life. And then later on, it's going to produce carbon and starts, when it reaches carbon, the sun is done. It's done for. Okay, carbon, oxygen. Some stars that are extremely heavy, though, they continue this process through their entire life until they produce iron. The trouble with iron, as you can see it in here, is sitting right on the bottom. You cannot make any more of it. You cannot fuse anything beyond iron to make the other elements. So how did we end up with other elements heavier than iron then on Earth? Here is the problem. Once a star makes iron, at that point, it does not make any more, and it actually starts to collapse in itself, and the nuclear reaction shuts down basically in its core, in which case, in this case, it's going to only make more and more iron, and the more and more it makes, basically, the faster it's collapsing on itself. That takes a fraction of a second while it's doing that. In other words, the minute the star starts making iron, it basically signed its own death certificate at that point. In other words, it's going to collapse on itself, and if it is big enough, it's going to go supernova. Because the supernova is extremely hot and violent, other elements are formed during that stage. So the rest of the elements are formed basically during this stage, okay? But this is how elements are formed. They're formed in there. So in fusion, what we do in this case, we take an element in here and we split it and we move down on this line. As we move down, we release that energy basically. And that is how the process works. This is, I'm sorry, did I say fusion? Fission, okay? Fission, we move down on this line and we're good, okay? Most of the fission applications, they are around uranium 235 or plutonium 239, down to just few elements in here, probably a little more than that. Ultimately, you would want to get all of this difference in here. And here is the fusion. Lighter elements fuse together to make heavier elements. In doing so, there is an excess of energy. In other words, the lighter ones, when you weigh them individually, they weigh more than the products. And the difference in mass is that mc squared. Multiplied by c squared, that is the energy released for you. The same thing in here. This one is heavier in mass by itself than the products. So in this case, the excess energy is what is released in the form of mc squared. You can clearly see that fusion is actually more efficient than fission. But that's basically, in a nutshell, what the diagram is saying in here. Again, this is the same thing as I was explaining in here. So uranium 235 are the fragments that form in here. And then the more energy in here, but that's the energy which is released mainly in the form of kinetic energy. And fusion is the opposite to it. And they both release energy. Both are produce energy. Here is how the fusion works, basically. In this case, I have two heavy isotopes of hydrogen. This is hydrogen, this is hydrogen. When I fuse them together, I get this element of helium. Obviously, the actual process is a little bit more complicated, even inside the sun, than this, okay? Here is what I was talking about, the missing mass. So you start with, see, the difference is slightly in here. So you start with the heavy elements and you get a lighter element out of it. And that is basically what the energy that you get from nuclear reactor or for bomb is. In this case, this is hydrogen bomb, actually. Hydrogen bomb uses this process, which is usually triggered by an atomic bomb. And then the difference in energy is much higher, because if you add the individual components of it, they are more massive than the helium that is formed. And the difference is mc squared in mass. Here is what's basically happens inside the sun. The sun, inside the core of the sun, or even basically what the hypothetical nuclear reactor should look like, you have to have the heavy hydrogen. This is a heavy hydrogen, deuterium is called, okay? You have to start with it somehow, okay? If you have it, that would be great, because then you can fuse two of them and they will produce with you an isotope of helium. So this is exactly what's going on in the sun. So you have an isotope of helium plus the extra hydrogen. This is the hydrogen. No, I'm sorry, this is the neutron, because you need the extra hydrogen. You need the other charge in here. So you need helium. So you have a neutron in this case plus a release of energy. This is not the main energy that you're going to get from this reaction. This is the one. This is the final stages when you get a lot of it. So again, now the combination of this two will give you at the end of the day a helium plus another neutron, okay? Plus tremendous amount of energy. In the sun, the process is a little bit different. And the sun, what's going on in here is that you have two protons, which is two hydrogen atoms, fusing together to form this exact isotope that I was talking about. When these two isotopes also meet, or one of them meets just with another proton, it forms this type of isotope of helium. Now, this type of helium, since now it's produced, can meet another this type of helium, and now you have basically four protons, and two neutrons forming this type of helium, plus in that case a release of two protons, not neutrons. So this similarity is very similar. In that case, produce more energy than this one. But it's still, this one is a very, very energetic. If you compare this equation to what happened to the uranium-235, this produces far more energy than the first one. So that is basically the how energy is produced inside a typical fusion reactor. Okay. The problem with it nowadays is it requires a lot of work. In other words, this process is not efficient in modern labs, okay? Because the biggest problem is how can you take two charges, these are charged particles, by the way, and bring them close from one another. There is a repulsion, and that repulsion stays almost all the way until they actually fuse. So it requires a lot of energy to confine them. This is this type of state of matter when they don't have electrons called plasma, and plasma confinement is a huge problem in physics. How can you confine plasma together? Because it's charged, and charges don't like to stay next to one another. So there is the obvious thing, which is magnetic field, but then you have to use tremendous amount of magnetic field to do it. That is one way of doing it, actually, and that is an experimental, actually, reactors. There is another way of also doing it, and that is to drop basically the droplets inside actually a very strong, what you call them, laser beams that can confine the plasma also, at least for a short while, so that the fusion happens. And both of them are extremely hard to do, actually, in the laboratory. So plasma reactors have not been successful. Other schemes include lasers are being considered. Deuterium pellets rhythmically dropped into this laser crossfires, heat used to produce steam. So basically, as you drop them, these are the deuterium droplets. They will be confined with the laser, with the laser beams in it. The other way that confining plasma is using magnetic field. Okay, that's another way of doing it. Okay, it's the tokamak nuclear reactors that use that, but they are still still not operational. They're still theoretical. Anyway, so this is basically the chapter. I know it's kind of small chapter, relatively speaking. Okay. So I will see you guys on Tuesday next week, same time, where we introduce the last chapters basically of the book. And then that's it, basically, in terms of content. Sounds good?
Yep.
Sounds good.
Sounds good.
Yeah.
Okay, very good. Okay, let me stop the recording now, and I will see you guys next week.